Okay, we've got a proof of mass, again, radius, big R. We've got a mass M1 on this side, a mass M2 on this side. What's the angular acceleration? Not looking for an immediate answer, but how do you get the angular acceleration? What's the first thing you need to determine? Well, now implicitly, we're assuming there's no friction, no dissipated force. Okay. Now it's M2R minus M1R. And the torque of this thing, your moment arm would be from here to here, and your force is acting here. So it's like and I left something out. M1G times R, right? So you got a force acting downward on the system, which might as well be acting here as here. There's a little bit of an error in that, and I'll explain. But okay, so you got Ri times the I vector, M1G times the J vector. Acting down. And over here, you have M2G times the J vector and a minus on I. I've written that kind of small because it's kind of a side calculation. Also, and the minus J here, isn't it? Okay. So those are vectors. You got Ri, you got minus M1G J, or M1G times negative J. Okay, you got negative R times your I vector, you got M2G times your J vector, assuming a horizontal vertical set of axes. Now, if you do the cross product, I times J is K, but you have a negative, so it's negative K, so that this torque is into the board. And here it's negative Ri crossed with a negative M2GJ, which gives you a positive M2GR times I cross J, which is K, which is out of it. Wait a minute. Yeah, which is out of it. Okay. So this torque is out of the board, this torque is out of the board, this torque is into the board. So I write them like this. We make the vector out of it just to be complete. Because you can avoid a lot of confusion if you explicitly write out these vectors. Okay. So there it is. There's your net torque. Now you know that to get your acceleration, you need your net torque. What else do you need? Well, L net over I, which of course is L net over of your MR squared. So what's the moment of inertia? A real important point here. Okay. All the mass of the hoop is out here on the rim. That's what a hoop is, an ideal hoop. Okay, if all the mass is out here on the rim, then all the mass of that hoop is at distance big R. So that the moment of inertia of the hoop is just big MR squared. Now, if you want to integrate it, or if you want to consider, divide this thing up into a million little pieces. Each piece is going to have its own mass times big R squared, because each piece is at distance big R. So if you write down the sum for all those pieces, you're going to have a big R squared as common to all of them. Okay, so you're going to have this little mass times big R squared, this little mass times big R squared, and so forth for a million of them. We're going to factor that million, you're going to factor that big R squared out of those million terms, and you're left with this mass plus this mass plus this, which is the total mass. Now again, I don't know how much work you did in calculus with breaking things down incrementally and working from local to global, but you're going to have to start doing a lot of that. Okay. And it's usually kind of a push to try to get that done. So there you have it. Okay, so anyhow, that's a moment of inertia of a hoop. There's also a formula given in your text. If you've read your text, you got formulas for moments of inertia. Moment of inertia of a hoop or a hollow cylinder is big MR squared. Okay. Moment of inertia for disk is 1/2 big MR squared. Because a lot of the mass is concentrated, most of the mass isn't out here at the rim, it's concentrated between here and there. And there's more I could say, but I won't right now. Okay. And if you got a sphere, it's concentrated even more toward the center. Central axis, assuming it's rotating about its central axis. Simple integrals, you get those. In any case, you also have this mass and this mass. For text and problems and the problem set explain why that's the case. If I want to apply a torque to this thing to rotate it, and let's just say these two masses were equal, so we don't have to worry about the torque exerted by the two masses. Now we're exerting all the torque. Then the energy of this mass at angular velocity omega is what? It's m1 v squared, whatever v is. The v is r omega, so it's mr omega squared and comes out. Okay. I'm not going to, we just can't take the time to totally develop that. That's something you got to pick up from the text and the problems. But that's it. I'll give you some rules, but you want to understand why the rules apply, or you tend to forget the rules. Okay, so there's a moment of inertia. So now we can write down our acceleration. And I'm not even going to do that. But that's how you get to the acceleration. We just take this and divide by this. That's going to be a multiple of k. If instead of a hoop, this is a disk, There you have it. That's the easy way to analyze an Atwood machine. It's an important application, especially since we spent a lot of time observing an Atwood machine. Now, the Atwood machine we observed had essentially no mass in the pulley. For that Atwood machine, I equals M1 R squared plus M2 R squared. The torque equals this. So the acceleration equals this. If this is your acceleration, I'll keep the vector nature, and you could leave the arrow off of the acceleration, but just to remind us that acceleration is in the direction K. This comes down to times your acceleration gravity divided by the radius. So my question is now, in this case, this is the one you observed, you essentially had a almost massless pulley, very light plastic, most of it. Well, the mass wasn't totally negligible, and you'd be able to take your data and actually determine what the moment of inertia of that pulley is. Okay, it's going to give you some anomaly in the ideal analysis, but what would the linear acceleration be? If M2 is greater than M1, what's the acceleration of M2? Well, the string is unraveling at the same speed as the rim of the pulley. So that turns out the acceleration, what we call the tangential acceleration, That's acceleration you would feel, let's say you're in a car around a circular track. You have a centripetal acceleration toward the center. You're being pulled toward the center, or you wouldn't be moving in a circle. You'd be moving in a straight line. You also can accelerate on the curve. Okay, of course, when you accelerate, your speed increases, so your centripetal acceleration increases. But that's not relevant to how fast or to the rate at which your velocity is changing, okay, or your speed. Okay, so you can speed up on that curve, and that speeding up, there's an acceleration there. The acceleration on the curve is tangent to the curve. It's always forward, you're always moving in the direction of the curve, so the forward vector is always tangent to the curve. So we say the acceleration is tangential. The acceleration of the rim of the pulley. Okay, acceleration is the tangential acceleration of the rim of the pulley. And what is the acceleration of the rim of the pulley? Okay, so we got a good answer to this question. I think it'd be easily be written. You go our time to that, it doesn't matter. Okay. So what is alpha times R? Well, there's alpha. M2 minus M1 over M2 plus M1 times G. And that's exactly what you get if you figure out what the net force is and divide by the total mass. The net force is M2G minus M1G, which is your M2 minus M1G, and your total mass is M2 plus M1. Now that's a really important connection. And it's pretty illuminating. So you really want to try to understand that. You want to understand this whole argument. Okay. Now, related stuff. First of all, intuitively, why M1R squared and M2R squared? Is this system any more difficult to accelerate with a torque than it would be if M1 was sitting here and M2 was sitting here? They would still have the same acceleration. Okay, although the acceleration, once the thing starts rotating, will be tangential rather than straight up. But the energy relationships are going to be exactly the same. Now, I could develop that in detail, but we really need to talk about several other things. So, you're going to need to think about that a little bit. And that, that question is brought out by some of the problems in the assignment. Okay. Another thing that's often a little bit confusing, and this is where we get into a little bit of angular momentum. First of all, let's take the simplest. This is a light rod, but I don't want it to be light. I want it to have a moment of inertia. A light rod with moment inertia 1/12 big ML squared. There's a simple integral. Your book doesn't, you should understand it. Okay. And we have a mass here. Mass M moving with velocity V perpendicular to the rod. What's the angular momentum of this mass relative to the axis of rotation? Okay, as expected, they told me what the impulse is. Okay, now in a roundabout way, I kind of had to drag it out. Okay, but the impulse it's M delta V. Okay. Thinking too hard about the signs of these things. Then delta V is MV, and that's not right. Your delta V is negative V, right? Okay. Now, why do you have an impulse? These things interact. Okay. This thing slows down. So that's the impulse delivered to the mass. The impulse exerted on the rod, that'll be the negative of that, which is plus M. You want to think through that. Okay. What's the force on the rod? You know the force is going to be in this direction. Okay. And what force does the rod exert on the mass? It exerts a force in this direction. So what force does the mass exert on the rod? What's the direction of the force of the mass on the rod? It's in this direction. Newton's third law, I think. So you can reason that out pretty easily. I wasn't very careful when I wrote it down. That's the way you work it out. And intuitively, it's obvious. It's going to be a positive impulse if upward is your positive direction. Okay, there's your impulse. Okay. So what is angular impulse? First of all, your impulse is average force times delta T, which means the integral of F with respect to T. Okay. And this is the force exerted by the mass on the rod, because that's the force that we're trying to get. Okay. So what's the angular impulse? Average torque times delta T. Definition of angular impulse. If you don't know what the definition of impulse is, the definition of angular impulse, review how we derive these things just from equations of motion. In the case of okay, and how that preferably how that extends to the integrals. That's fundamental, it's foundational, because we can't analyze this collision very well without understanding that. So make sure you understand it's very, very straightforward consequence of Newton's third law and equations of motion. Okay, whether the equations of rotational motion, angular motion, with equations of linear motion. This case. Okay, angular impulse is average torque times delta T. That's it. You've got to understand how that is derived. And of course, that's equal to the change in angular momentum, change in I omega. What's the average torque exerted when this thing collides here? In terms of the average force. So if you know the average force, then you're going to get the average torque. Well, the average torque is the R vector crossed with the average force vector, which equals well, the average force is mv over delta T. What's R cross mv? Well, R cross V is here, right? The magnitude of R cross V is omega. Better go to the linear or the magnitude of the torque per minute. Okay. The average torque then in this case is MVR over delta T. And what's MVR? It's the magnitude of the angular momentum. That one, which is to read it. If you use L symbolize your angular momentum, it's L over delta T. Now, if I work the vectors in, a little more complicated, but R cross V gives you the direction of L. And I'll wave my hands a little bit. L is the angular momentum of mass M. So this tells you that the angular momentum of the mass M our conclusion is angular momentum of mass M is M times R plus V. Okay. And that's something we kind of know. Now we want to contrast that. This is one of the confusing things about angular momentum. Take the same situation. Now, this mass is moving with this velocity. This angular momentum is no longer mv times the r vector. It's going to collide here. This is not our vector. If this distance is the same as it was in this picture, and here we can see this picture. Okay. Can't even see my, come on, Zoom. Give me, okay, where are we? Can I see this? Yes. Okay. I need a bigger screen there, but it'll block people's view. Okay. This is the same collision point that was. If we do M, well, R cross MV, we're not going to get the same thing we got over there. Assuming that the magnitude of V is the same, the magnitude of R is the same, we're going to have a sine theta involved in this thing. Okay? Because the angle between the R vector and the V vector is no longer 90 degrees. So what are we going to do about that? Well, the short answer is, and I'll try to make sense of it. R vector has to be perpendicular to the path of the particle. So this is our R vector. Right here's your R vector. If you want it to be perpendicular, if you want to just do MVR, we want to use L equals MVR. I should have qualified this. And MVR. However, this can be our R vector if we use vector representation. If we use L equals R cross MV, And R can be any vector. From the axis of rotation to the path of our mass. So again, but here's our path. We could use any of these vectors. We could use the R vector here. We could use the R vector here. We could use the R vector here. It makes no difference. Why does it not make any difference? We could use the R vector down here. Well, what's the magnitude of R cross V? This means that the magnitude of R cross V should be the same for any of these vectors. So what we do is we say, okay, here's our axis of rotation. Here's M. Here's V. Any R vector. It's going to make some angle theta with the D vector. So what's your expression for R cross MV? Well, R cross MV is going to equal MVR sine theta. Okay. Now I was a little clumsy when I labeled theta the way I did. What I'm going to do this angle's still theta, but I don't want to put the label where I did. I'm going to say that, okay. There's your angle theta. What I do is I draw a perpendicular from this point down to the path of V. Okay. And I'm going to call this line is R min. It's the shortest possible R vector, isn't it? Shortest distance from a point to a line is at a perpendicular to the line. Should be able to prove that. Okay. But it's intuitively pretty obvious. If you're in a field and you see a bull charging at you, you go directly to the fence. You don't take a longer path here, a longer path there. Now, kind of depends on what direction the bull's charging you from. You want to get to the fence as quick as possible you go straight toward the fence, which is at a perpendicular to the fence. Okay, I like to use that analogy, even though it isn't a great one. Okay. And this equals MV times R min. Because what? Sine of theta is R min over magnitude of R, right? So magnitude of R sine theta is R min. So, as I said, it doesn't matter what R vector you use. Now, I don't know how useful that's going to be to you if you're confused about the whole idea of why the angular momentum or the moment of inertia or the torque of a point and so forth depends on the closest point of the path to the axis of rotation, or the point of rotation, depending which it is. But that's why. Doesn't matter what R vector you use, you do the cross product, you always get a magnitude of MV times R min, and the only difference between the magnitude and the vector is got to be in the direction of R cross V. In this case, it would be into the void. No. R cross V, so be out of the void. Okay, well, hopefully that makes sense. Couple of important points I wanted to make. You know, the idea of the Atwood machine, which is an important example. And the whole thing about closest point on the path. It's what you use to determine the angular momentum. Or the torque of a force, similar argument. It comes down that little triangle. Okay. Here's the Earth and here's you. And here's me. Which one of us do you think experiences a greater gravitational force due to the Earth? Okay, everybody has good intuition on this. If this is the Earth, then if I'm here and you're there, you're going to feel the bigger force or the Earth because you're closer. By analogy with magnets, and it's a very loose analogy because magnets do a lot of things gravitation doesn't. They don't act the same way. They're dipoles and all that stuff. And you know, be working that out more in detail second semester. But everybody said, well, this person's going to feel more than I will. Okay, you are going to feel more than I do because you're closer. And if you're closer to a magnet, you're going to feel more force. And if it's between two magnets or between a magnet piece of metal. So also I asked, what's the direction of the force? I asked you to draw the vectors. So everybody did a pretty good job with that. Everybody drew a vector toward the center of the Earth. And the vector for you is bigger than the vector for me. And these intersect at what hopefully is the center. It's really interesting what happens if you have a tunnel through the Earth and see what happens to the gravitational field as you move closer to the center. It's pretty cool. It actually increases for a while, then it decreases because by the time you get to the center, different parts of the earth are pulling on you equally in different directions, and you have no force. Of course, you're also dead because of pressure and temperature. So you can't really get there. Then we can't drill a hole. We've gotten maybe we're approaching 0.5% of the distance from here to here with the deepest holes we can drill. It's problematic. Mechanical engineering and a materials problem. It gets hotter, so it stresses your drilling apparatus. You go deep enough, it'll melt it. Got real problems there. Okay, well, that's not particularly relevant, but it gives you a little bit of context. Okay, so how about this? If I'm twice as far from the center as you are, what's the ratio of our forces? Well, let's say you're twice as close. And that's not the case with the picture we've drawn, but you're twice as close. To the center. I'm going to call myself number one. We're going to assume equal masses because I never postulated that. Okay. If you're much more massive than I am, then your vector is going to be longer than if you're around my mass. Nobody's, I don't think, has less than my mass. So what do you think? How many times as much force are you going to feel as I will? Okay, I got one guess of one answer of 4 times as much, and everybody else says, I don't know. Okay. Which, kind of reflects a little bit on science and education in our curriculum. But that's not unexpected. So don't feel bad about it. Nobody ever told you, nobody ever thought about it, because I don't want to get into it. Okay. People with good aptitudes really need to see a lot more than they're seeing. Okay, still, here's the idea. Okay, here you got, let's say, here you got the mass. Let's call this mass M. Okay. I draw a sphere around this mass of radius capital R1. What's the surface area of the sphere? Who knows how to get the surface area of a sphere? Hopefully you would have done the integral in your calculus course, because it's kind of neat. But actually that integral might be a little more appropriate to multivariable calculus. I mean, it can be done. It's just a surface area integral. Except you did, no, you wouldn't have done it. Okay. Okay, surface area. We'll call that F1, surface area 1 and 4 pi R1 squared. Well, let's do another one that's some other distance, R2. clearly S2 over F1 is R2 over R1 squared, right? Now, and this isn't a great analogy, but it still gives you a picture that's going to be really useful. Let's say instead of a mass at the center of the sphere, you've got a little pellet. Okay. And that pellet is at, let's say, 100 million degrees Kelvin, Celsius, doesn't matter. Okay. 273 degrees out of a million doesn't make any difference. So that pellet is glowing, a lot of energy coming off that pellet, right? So let's just say it's glowing at an equal temperature for some time, okay? Then what's happening to that energy? It's radiating outward, isn't it? And it's light, it's electromagnetic energy. Okay, it's actually from heat. But, we'll talk about that in the wood. Yeah, spring semester. If you don't understand it, but so we've got this energy flowing outward. Now, how much energy flows through this sphere in a nanopicosecond or microsecond, whatever you want, and how much flows through this sphere? Assuming thing is continuing to glow, it's been glowing long enough at whatever constant output you want to postulate. Okay, it's been glowing long enough that the energy has reached the outer sphere. So which sphere is going to have more energy passing through it? One, two, same. One. Still no vote. Okay, well, you're wrong. Okay, it's okay though. Okay, well, think about it. The energy flowing through here is the total energy that was produced in the center in that 1 microsecond. Okay. So the energy flows through here in a microsecond is the energy that was produced here sometime earlier. Okay. Energy flowing through this sphere is the same in a microsecond, let's say. It's the same as the energy that was produced here in 1 microsecond, isn't it? In other words, all the energy that's produced here at some instant passes through this sphere. At some later instant, all that energy passes through this sphere. Unless there's something dissipating the energy, and we're assuming an ideal situation where nothing is dissipated. Okay? Does that make sense? If we assume that no energy is being dissipated anywhere between here and wherever, then the energy passing through here in a microsecond is the same as the energy passing through here in a microsecond. Whatever time it takes the energy to get from here to here, it's speed of light. And the energy flowing through here in that microsecond is the energy that flew here, that flowed through here in the microsecond that much time earlier. That much earlier. Okay, so if you accept that the energy flowing through these things is the same in both cases, that assumes a constant source here. It assumes a constant source has been active long enough that the energy has gotten here. And whatever energy flows through this sphere has to then flow through this sphere, because where's it going to go? It's not being dissipated, it's not being accumulated any place. It's got to keep going outward. Okay, well, lots of things behave like that. Electromagnetic fields, electrostatic fields. and gravitation. Gravitational fields. And we know that gravity, and we just learned this within the past decade, and somewhat less than a decade, through the LIGO interferometer, and explain that to you this morning too. We know that they're gravitational waves, like they're electric waves, electromagnetic waves. Okay. So there are a lot of analogies with gravitation. There are a lot of places the analogies break down. As far as this is concerned, you have this ratio of surface areas. Now, which surface is going to be illuminated most brightly? One or two. That's probably where your answer before came from. Okay. Intuitively, you're closer to the light bulb, you're going to get more energy, right? Yeah, more energy per unit area. So if you're trying to read a newspaper by that energy, it's going to be easier to read it here than it is here. Unless the energy is right here, it burns you and the newspaper up. Okay, so you get the idea. It's going to be more intense, more energy per unit area here, less energy per unit area here. So intensity I'm going to use the word flux. Okay. You got an energy flux flowing outward. It's a constant flux, but it's flowing through bigger and bigger areas. So the intensity equals flux per unit area, so that what's I2 over I1? Okay. Well, it's going to be flux over area 2 divided by flux over area 1. Since you're dividing by the areas, it's going to reverse the R2 and the R1. So that if R1 is less than R2, you're going to get greater intensity. It's an inverse proportionality. Proportionality is another thing you guys deserve to have pondered from the age of 12 on. Okay. Yeah, started pondering it in middle school. Had a really good teacher. Okay, anyway, there you have it. You put all that together, and it makes plausible Newton's law of universal gravitation. It says I better find some clean board to write on. Okay, look the back of this now. Oh, it's no fair. That's a bit low. Too much. Okay, hang on. Third quarter. Yeah. Well, that's all right. All right. Okay. Let's assume a point mass. A uniform sphere acts like a point mass with all its mass concentrated at the center. So it's like the Earth acts just the same as it would if all its mass was concentrated at the point at the center. Not really, because the Earth isn't totally uniform. It's pretty close. So anyhow, we got a bit mass, let's say big M here, and a mass little m here. These masses exert forces on each other. got a force here. Force on mass big M exerted by little m. And an equal and opposite force from little m exerted by big M. So it'll be a straight line. Here's our R vector. Okay. Force. V is just a proportionality constant. It's equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. The more mass you've got here, the more force there is, and the more mass you've got here, the more force there is. So force is going to be proportional to the product of the two masses. Multiply that by the R vector divided by the magnitude of the R vector, and you put a negative sign in front of it because it's a force of attraction. Now this is the R vector for the force exerted on this mass by this mass. The R vector for the force exerted by big M on little m would be from big M toward little m. And there's your law. It says stuff that's obvious. If you understand that flux picture, it's like the gravitational influence expands outward over bigger and bigger spheres, whose surface areas go as their radii. It's inverse to the surface area because you have less intensity with the bigger surface area. This is just a unit vector in the direction of R. So it's just a unit vector tells you what direction things in. You got a negative sign here. And big G is just another big G. Better to write a 1, try to write a 6 and do it. Okay. Units of big M and little m will be kilograms. Units of R will be meters. So that when you multiply this unit by the kilogram squared you get here, over the meter squared you get here, they divide out and you get newtons. You could express it in other systems of units, but that's probably the one that's most appropriate in most situations. Okay. From this, you get circular orbits. You get a lot of stuff that I'll talk about, but we're out of time, so I'm not going to talk anymore. Okay. You want to know that, you want to know that picture. So be sure you review that picture. Be sure you can draw that picture when you come in the next time and write the law. Pretty simple. There it is, in case it was blurred when I was explaining it.